The birthday paradox is a surprising idea in probability that quietly challenges our intuition. At first, it seems impossible. In a room of just 23 people, there is more than a 50% chance that two people share the same birthday. Most people expect that you would need many more people, but the mathematics behind this paradox shows how probability can be counterintuitive, subtle, and even meditative. To understand the paradox, consider this. Instead of asking whether any one person shares your birthday, we ask whether any two people in the room share a birthday. With 23 people, there are 253 possible pairs. Each pair is an opportunity for a match. Even though each individual chance is small, the total probability grows quickly as more pairs are considered. This is the key to the paradox. Our intuition often focuses on single outcomes, while probability considers all possibilities quietly and systematically. Take a moment to visualize it. Imagine a small room with people scattered around. Each person has a birthday somewhere in the year. At first, it seems unlikely that anyone shares a birthday. But as you look at all the possible pairs, the odds shift. Probability is not about what we expect. It is about the hidden structure of possibilities. This gentle insight is calming, reminding us that reality often contains layers beneath what we see. The birthday paradox is also connected to larger ideas in probability and statistics. It shows how small numbers can produce unexpected outcomes, and how combinations, rather than single events, shape likelihood. This principle is used in computer science, cryptography, and risk analysis. Understanding it allows us to see patterns where randomness seems to dominate, quietly unveiling order in apparent chaos. Take a moment to reflect on the philosophical side of the paradox. It demonstrates that intuition can mislead us, even in something as simple as birthdays. Life is full of hidden patterns and probabilities that may not be obvious at first glance. Probability encourages patience, observation, and reflection. It invites us to slow down and consider all the possibilities before making assumptions. Another fascinating aspect of the birthday paradox is its connection to larger-scale probability problems. In cryptography, for example, the birthday attack uses a similar principle to find collisions in hash functions. The paradox demonstrates that rare events can happen more often than intuition suggests, and that understanding probability can reveal hidden risks or opportunities. Mathematics, in this sense, becomes both practical and meditative. Take a moment to imagine birthdays scattered along a timeline. At first, each seems isolated and independent, but as you consider every pair, connections appear. The paradox is not chaotic. It is structured, gentle, and full of subtle surprises. It teaches us that even when outcomes seem unlikely, patterns can emerge quietly, waiting to be noticed. The birthday paradox also inspires wonder about coincidences and chance in everyday life. When we meet people who share birthdays or notice unexpected coincidences, probability reminds us that these events, while surprising, are part of a quiet, underlying order. Life contains patterns, not always obvious, but present if we pay attention. Finally, the paradox encourages reflection on perception. Our minds are drawn to what is visible, immediate, and obvious, while probability asks us to consider the invisible, systematic, and hidden. This gentle shift in perspective is calming and thought-provoking. It reminds us that there is beauty in the unseen, and that mathematics is a tool for exploring hidden truths in a quiet, reflective way.
Pascal's triangle is one of the most elegant structures in mathematics. It looks simple at first, a triangle of numbers, starting with 1 at the top. Each number in the triangle is created by adding the two numbers directly above it. At first glance, it seems like a simple counting exercise. But as you look closer, patterns begin to emerge, quietly revealing a world of order, symmetry, and surprising connections. Pascal's triangle is not just numbers, it is a reflection of the hidden harmony that mathematics can uncover. One of the most fascinating aspects of Pascal's triangle is symmetry. The triangle looks the same on the left and right sides. Each row mirrors itself perfectly, a gentle reminder that balance exists even in abstract structures. This symmetry is calming, as if mathematics itself is quietly reassuring us that there is order even when numbers grow large and patterns seem complex. Pascal's triangle also contains many hidden patterns. For example, the numbers along the edges are always 1, but the second numbers in each row are the natural counting numbers, 1, 2, 3, 4, and so on. Diagonal lines of numbers form sequences of triangular numbers, tetrahedral numbers, and other fascinating shapes. Each line, each diagonal, each layer contains relationships waiting to be discovered. It is like looking at a quiet forest and realizing that every branch, leaf, and root follows an invisible rhythm. Take a moment to consider the sums of each row. The sum of numbers in each row is a power of 2. The first row sums to 1, the second to 2, the third to 4, the fourth to 8, and so on. These simple sums connect Pascal's triangle to exponential growth, probability, and even the binary systems that power our computers. A simple triangle of numbers quietly reflects the laws of the universe and the patterns of growth. Pascal's triangle is also connected to combinatorics, the study of counting and arrangement. The numbers in the triangle tell us how many ways we can choose objects from a set, such as picking 3 apples from 5, or arranging objects in different orders. This connection links a visual pattern to real-world problems in probability, decision-making, and even genetics. The triangle is not only beautiful, it is useful. Another fascinating feature of Pascal's triangle is the presence of Fibonacci numbers. By adding numbers along diagonal paths in the triangle, you can create the sequence of Fibonacci numbers. This hidden connection between two different mathematical structures is quiet, subtle, and profound. It reminds us that mathematics is interconnected, full of surprising links that are both logical and beautiful. Imagine tracing the triangle with your finger, moving along diagonals, sums, and patterns. Each path reveals a new secret, a new relationship. It is a calm journey through numbers where every step uncovers something unexpected but harmonious. Pascal's triangle invites gentle curiosity, encouraging us to notice small details while appreciating the larger structure. Pascal's triangle also appears in nature. It describes patterns in probability, arrangements of petals, branching of trees, and even the structures of crystals. The triangle shows that even abstract mathematics can reflect the world around us, quietly revealing the hidden order in seemingly random patterns. Take a moment to reflect. A simple triangle of numbers, created with a few rules, contains endless surprises. It shows symmetry, harmony, and hidden beauty. It connects to infinity, growth, and the patterns of life itself. Pascal's triangle is a reminder that mathematics is not only logical, it is also gentle, reflective, and quietly magical.
Complex numbers are numbers that combine the real and the imaginary. They might sound strange at first, but they are very powerful. A complex number has 2 parts, the real part, which we can understand easily, and the imaginary part, which comes from numbers like I, the square root of -1.
For example, 3 plus 4i is a complex number. The 3 is real and the 4i is imaginary. Together, they form a single number that can describe much more than either part alone. Imagine you are standing on a flat field. You can walk forward or backward. That is like a real number, one direction along a line. Now imagine you can also move sideways at a right angle. That is like an imaginary number. A complex number combines both directions, creating a new space, a plane where movement is richer, more flexible, and more complete. Mathematicians call this the complex plane, and it is a way of seeing numbers in two dimensions instead of one. Complex numbers are not just abstract ideas. They are used to describe waves, vibrations, and oscillations. They appear in sound, light, electricity, and magnetism. Engineers use them to design circuits and signals. Physicists use them to understand quantum mechanics, where particles behave in ways that ordinary numbers cannot fully describe. Complex numbers are a bridge between imagination and reality. They show that even strange, abstract ideas can have very real effects. Imagine you are standing on a flat field. You can walk forward or backward. That is like a real number, one direction along a line. Now imagine you can also move sideways at a right angle. That is like an imaginary number. A complex number combines both directions, creating a new space, a plane where movement is richer, more flexible, and more complete. Mathematicians call this the complex plane, and it is a way of seeing numbers in two dimensions instead of one. Complex numbers are not just abstract ideas. They are used to describe waves, vibrations, and oscillations. They appear in sound, light, electricity, and magnetism. Engineers use them to design circuits and signals. Physicists use them to understand quantum mechanics, where particles behave in ways that ordinary numbers cannot fully describe. Complex numbers are a bridge between imagination and reality. They show that even strange, abstract ideas can have very real effects. Think about a wave on the ocean. It moves up and down, forward and back. A single number cannot describe this motion completely, but a complex number can. The real part describes one aspect of the motion, and the imaginary part describes the other. Together, the complex number captures the full behavior of the wave. This is why complex numbers are so important in mathematics and science. They allow us to see patterns that would otherwise be invisible. Complex numbers also revealed the hidden beauty of mathematics. Using them, mathematicians discovered relationships between numbers, shapes, and patterns that are elegant and surprising. One famous example is Euler's formula, which connects the most important numbers in mathematics, e, I, and pi. This formula shows a deep connection between real and imaginary numbers, between growth and rotation, and between the finite and the infinite. It is considered one of the most beautiful equations in all of mathematics. Take a moment to imagine the complex plane. Every point on the plane is a complex number. Every motion, wave, or oscillation can be represented. The plane stretches infinitely in all directions, showing how mathematics can capture movement, change, and rhythm. Complex numbers let us explore this infinite space carefully, calmly, and logically, while also appreciating its beauty and mystery. Complex numbers also challenge our intuition. In the real world, we cannot see imaginary numbers directly, but by combining them with real numbers, we can understand phenomena that we can observe, like alternating current, vibrations, and quantum waves. This shows that even the most abstract ideas can have concrete effects. Mathematics allows us to explore hidden layers of reality, layers that cannot be touched, but can be understood. From complex numbers, we can move toward even deeper mysteries, like functions, waves, and the strange behaviors of systems that change over time.
Complex numbers are the foundation for much of modern mathematics and physics. They show us that numbers are not limited to counting objects. They can describe movement, change, and even the invisible forces of the universe.
Simulations and mathematical reality quietly invite us to reflect on the delicate relationship between numbers, patterns, and the universe. At first glance, simulations may seem like mere computer experiments, models run on screens. Yet they are far more profound. They reveal how mathematics can mirror reality, predict behavior, and even challenge our understanding of what is real. This gentle interplay between abstraction and experience encourages slow, meditative contemplation. Take a moment to imagine a simple computer simulation. Particles move across the screen according to a few basic rules. Each step is calculated precisely, yet the resulting motion can appear chaotic, organic, and surprisingly lifelike. This quiet emergence of complexity from simple rules mirrors phenomena in nature, from weather patterns to flocking birds. Mathematics acts as the invisible hand guiding these systems, revealing subtle harmony beneath apparent randomness. Simulations also help us explore systems too vast or intricate to observe directly. Galaxies colliding over billions of years, climate patterns evolving over decades, or molecules interacting in a cell. These are all captured in mathematical models and run in virtual spaces. By observing these simulations, we gain insight into processes that would otherwise remain hidden. Reflecting on these virtual universes encourages calm curiosity and patient, reflective observation. Philosophically, simulations raise quiet, thought-provoking questions about the nature of reality. If we can recreate behaviors, structures, and even entire worlds through mathematics, what does this suggest about the universe itself? Could the cosmos be thought of as a kind of simulation, guided by underlying rules and patterns that are essentially mathematical? While these ideas are speculative, they gently expand our perspective, encouraging contemplative wonder rather than anxiety. Take a moment to imagine standing in a vast virtual world, watching particles, planets, or abstract forms interact according to precise rules. Every movement is predictable, yet collectively they create patterns too intricate to follow completely. This mirrors life itself, deterministic in principle, complex and subtle in practice. Observing this quiet complexity encourages mindfulness, reflection, and meditative engagement with thought. Simulations also illustrate the subtle beauty of mathematics itself. Simple rules, when applied iteratively, can produce fractals, emergent behavior, or dynamic patterns. These digital or conceptual creations are more than experiments. They are exercises in curiosity, patience, and quiet observation. They demonstrate that complexity can arise naturally from order, a gentle reminder that the universe may be organized in ways both comprehensible and mysterious. Even beyond computers, the principle of simulation extends to human thought. Models of population growth, economics, or ecosystems allow us to explore hypothetical scenarios, test ideas, and gently predict outcomes. Each model is a mathematical lens, focusing attention on patterns and structures that might otherwise remain unseen. Reflecting on these processes cultivates calm awareness and thoughtful curiosity about hidden connections.
Mathematical models of the universe quietly reveal the hidden structure of reality. They are the tools that scientists and mathematicians use to describe how galaxies move, how stars are born, and how the cosmos evolves. At first glance, these models seem abstract and distant from daily life, but reflecting on them slowly can be deeply meditative, offering a gentle perspective on the harmony underlying the universe. Take a moment to imagine the night sky. filled with countless stars. Each star moves according to the laws of physics. Their motions might seem random, yet they follow patterns that can be described using mathematics. Gravity, electromagnetism, and quantum mechanics provide rules for these movements. Mathematical models condense these laws into elegant equations, allowing us to predict and understand the behavior of cosmic structures. Observing this harmony quietly encourages awe and reflection. One of the simplest yet most profound examples is Newton's law of universal gravitation. It describes the force that draws objects toward one another. From falling apples to orbiting planets, this law quietly explains the motions we observe. Over centuries, it allowed humans to map the heavens, predict eclipses, and explore the universe in ways that feel both precise and meditative. Later, Einstein expanded this understanding with general relativity. Gravity is no longer just a force, it is the bending of space and time. Massive objects curve the space around them, guiding the motion of planets, light, and even galaxies. This gentle, counterintuitive idea shows that the universe is not flat and predictable in the way our intuition suggests. Instead, it has hidden curves and subtle structures that mathematics helps us reveal. Reflecting on these invisible curves invites quiet wonder and intellectual meditation. Mathematical models also help us explore the smallest scales. Quantum mechanics describes the behavior of particles that are too small to see. Equations capture probabilities, wave functions, and particle interactions. Though the world of quantum mechanics seems strange and counterintuitive, mathematics provides a steady, reliable guide. Observing these models is calming, as it highlights the hidden order beneath apparent chaos. Take a moment to imagine connecting the cosmos and the quantum world. Mathematical models act like invisible threads, linking the largest structures to the smallest. Through these models, we begin to see patterns and relationships that are not obvious at first glance. The universe becomes a tapestry of subtle connections, each thread guided by quiet mathematical rules. Reflecting on this structure encourages patience, curiosity, and gentle contemplation. Philosophically, mathematical models of the universe invite reflection on the nature of reality. They suggest that the cosmos is not arbitrary or chaotic, but structured, patterned, and understandable, at least in part. Yet the models are always approximations. They are tools for understanding, not complete representations of reality. This gentle awareness teaches humility, reminding us that even our most elegant equations capture only glimpses of the infinite complexity around us. Mathematical models also inspire creativity. By exploring equations, simulations, and abstract representations, we can imagine new possibilities, test hypotheses, and extend understanding beyond immediate observation. This quiet exploration is meditative, blending logic, imagination, and curiosity in a calm and reflective practice.
Chaos versus determinism is one of the most quietly fascinating ideas in mathematics and science. On the surface, determinism suggests that everything follows clear, predictable rules. If you know the initial conditions of a system perfectly, you can calculate its future exactly. Chaos, however, gently reminds us that tiny changes can grow into enormous differences, making long-term prediction almost impossible. Reflecting on this balance between order and unpredictability can be deeply meditative.
Take a moment to imagine a double pendulum. A pendulum attached to the end of another pendulum. Start it gently, and the motion seems simple at first. But soon, it twists and swings in ways that are impossible to predict by eye. This is chaos in action. Deterministic rules create behavior so sensitive to initial conditions that even the smallest variation leads to completely different outcomes. The motion is ordered, yet unpredictable, quiet, yet infinitely complex. Chaos does not mean randomness. Every swing of the double pendulum follows the laws of physics exactly. The underlying determinism is perfectly present. Yet, because our ability to measure and calculate is limited, the system feels unpredictable. This quiet tension, perfect order paired with practical unpredictability, is what makes chaos so mind-bending and reflective. It invites patience, observation, and thoughtful meditation on the subtle beauty of nature's rules. Philosophically, chaos versus determinism raises gentle questions about knowledge, control, and certainty. How much can we truly know? How much can we predict? Even if the universe is entirely deterministic, our limited perspective introduces uncertainty, reminding us of humility and quiet wonder. This balance mirrors life. While patterns exist, the unfolding of events often surprise us, creating both complexity and meditative reflection. Chaos theory also appears in nature in countless ways. Weather patterns, the growth of populations, and the behavior of fluids all exhibit sensitivity to initial conditions. Tiny differences, like a butterfly flapping its wings, can lead to large-scale changes over time, a phenomenon often called the butterfly effect. Observing these patterns encourages calm curiosity, a sense of awe, and gentle contemplation on the subtle beauty of nature's rules. Take a moment to visualize a leaf floating on a stream. Small ripples, invisible currents, where the slightest breeze can shift its path dramatically over time. The motion is deterministic, yet chaotic, both simple and infinitely complex. This observation is reflective, inviting us to notice the interplay of order and unpredictability in the world around us. Chaos and determinism also influence mathematics itself. Simple equations, iterated over and over, can produce fractals, infinitely detailed, self-similar patterns. These are examples of order emerging from deterministic rules even when outcomes appear chaotic. The quiet repetition and unfolding of structure in fractals mirror the meditative experience of contemplating chaos. Complexity arises naturally, without forcing, and invites reflection and calm observation. Philosophically, the interplay between chaos and determinism mirrors the tension between certainty and uncertainty in life. Systems can be perfectly ordered and yet produce surprising outcomes. Reflecting on this quiet balance encourages mindfulness, patience, and intellectual humility. It reminds us that understanding is a process, not a destination, and that beauty often lies in the interplay of predictability and surprise.
Turing machines quietly changed the way we think about computation, logic, and the very nature of thought. Conceived by Alan Turing in the 1930s, they are abstract devices designed to explore what it means to compute. At first glance, they seem simple: strips of tape, a moving head, and a set of rules. But their implications quietly stretch across mathematics, philosophy, and the foundations of artificial intelligence. Imagine a long tape, divided into squares, each square holding a symbol. A head moves along the tape, reading and writing symbols according to a set of instructions. This machine, though abstract and mechanical, can perform any calculation that a modern computer can. Turing's insight was profound. A simple, logical system could represent the full power of computation. Reflecting on this calmly, we see the quiet elegance of rules giving rise to infinite possibilities. Turing machines also reveal limits. Some problems cannot be solved by any machine, no matter how clever.
The halting problem asks whether a machine will ever stop when given a specific program and input. Turing proved that there is no universal method to answer this question for all programs. This gentle paradox teaches humility, reminding us that even the most systematic reasoning has boundaries. Some mysteries quietly elude computation, inviting reflection and meditative curiosity rather than frustration. Take a moment to visualize the tape and the head moving slowly, writing symbols, reading patterns, and following instructions. Each step is deterministic, yet the patterns can grow infinitely complex. This quiet unfolding of logic mirrors life in some ways. Simple rules lead to rich, unpredictable outcomes. Observing this process is calming, inviting thoughtful attention to the subtle structure of systems. Turing machines also form the conceptual birth of artificial intelligence. By abstracting the process of calculation and decision-making, they laid the foundation for machines that can simulate reasoning, solve problems, and even learn. Modern AI, in all its complexity, quietly traces its roots to these simple, elegant machines. There is a meditative beauty in seeing how abstraction transforms into tangible reality over time. Philosophically, Turing machines encourage reflection on the nature of thought, consciousness, and intelligence. If a simple machine can compute anything computable, what separates human reasoning from mechanical processing? Where do creativity, intuition, and insight emerge? These quiet questions invite reflection, patience, and a gentle sense of wonder at the mysteries of mind and computation. Even practical applications are profound. Algorithms, data processing, encryption, and programming languages all rely on principles derived from Turing's work. Yet beneath the technical utility lies quiet elegance. A simple framework that can model infinite processes, explore deep logic, and reveal fundamental truths about computation and reasoning. Finally, Turing machines remind us that mathematics is not just about numbers. It is a way of thinking, a tool to explore both reality and abstraction. They quietly demonstrate how logic, patience, and creativity can uncover the foundations of computation, intelligence, and even artificial minds. The idea of an infinity of dimensions is both strange and quietly mesmerizing. In our everyday experience, we move through 3 dimensions: up and down, left and right, forward and backward. Time adds a 4th subtle dimension. But mathematics allows us to imagine spaces with infinitely many dimensions, spaces that are abstract yet rigorously defined. Exploring these dimensions gently stretches the mind, inviting calm reflection and quiet wonder. Take a moment to imagine a line. It has 1 dimension, length. Now imagine a square, which adds a 2nd dimension, width. A cube adds a 3rd, height. Each step adds a new way to measure space. Mathematicians ask, what if we could continue this process without end? What if space could have hundreds, thousands, or even infinitely many directions at once? Though we cannot visualize this directly, we can understand it through equations, logic, and patterns. Infinite dimensional spaces appear in many areas of mathematics. For example, functional analysis studies spaces where each point is a function rather than a simple number. Each function can be thought of as a dimension. These spaces are vast and intricate, yet mathematics provides tools to navigate them calmly, systematically, and elegantly. Even though we cannot see these dimensions, we can understand their structure and behavior through patterns and reasoning. Imagine a gentle breeze moving through an infinite dimensional space. Each function is a direction the breeze could flow, and each change, no matter how small, subtly affects the overall structure. This analogy captures the quiet complexity of these spaces. They are infinitely detailed, yet governed by rules that mathematicians can explore and understand. Observing this process is meditative, encouraging patience and reflective thought. Infinite dimensions also appear in physics. Quantum mechanics, for instance, describes particles in terms of wave functions that exist in vast, abstract spaces. Each point in these spaces represents a possible state of the system. The behavior of the universe at its smallest scales unfolds in these invisible, infinite-dimensional spaces, revealing subtle order hidden behind apparent randomness. This quiet connection between mathematics and reality invites awe and gentle contemplation. Take a moment to reflect on how infinite dimensions challenge intuition. We are used to thinking in 3 dimensions, and adding a 4th is already difficult. Yet mathematics allows the mind to extend far beyond the visible, to explore structures that seem impossible. The infinity of dimensions is not chaotic. It is carefully organized, with rules, patterns, and harmony that encourage calm and reflective exploration. Philosophically, the infinity of dimensions encourages humility and curiosity. Even if we cannot perceive these spaces directly, we can engage with their logic and beauty. They remind us that reality may be far richer and subtler than our senses could just. This quiet awareness fosters patience, wonder, and a meditative appreciation for the hidden complexity of existence. Even in everyday mathematics, higher dimensions provide insight. Multidimensional data, networks, and systems can be analyzed using principles from infinite dimensional spaces. Patterns emerge, structures reveal themselves, and the world becomes slightly more understandable, more connected, and more harmonious. Observing these patterns is calming, like following gentle threads through a vast tapestry.
Non-Euclidean geometry quietly stretches the imagination. It asks us to imagine worlds where the familiar rules of straight lines, angles, and planes no longer apply. In Euclidean geometry, taught in schools, parallel lines never meet. The angles of a triangle always add to 180 degrees, and space feels flat and predictable. Non-Euclidean geometry challenges these assumptions, revealing hidden layers of mathematical beauty and curiosity. Imagine walking along 2 parallel lines on a vast, gently curved surface. In Euclidean geometry, you expect them to remain the same distance apart forever. But in a non-Euclidean space, the lines may slowly converge or diverge. They may meet far away or curve apart endlessly. This subtle shift in intuition quietly invites reflection, showing that space itself can behave in ways that feel strange, yet are perfectly logical within the rules of mathematics. There are 2 main types of non-Euclidean geometry, hyperbolic and elliptical. In hyperbolic geometry, space curves like a saddle. Triangles have angles that add to less than 180 degrees, and parallel lines can diverge infinitely. In elliptical geometry, space curves like a sphere. Triangles have angles that add to more than 180 degrees, and there are no true parallel lines. All lines eventually meet. These gentle deviations from the flat world we know demonstrate that geometry is not fixed. It adapts to the shape of the space itself. Take a moment to visualize a triangle on the surface of a globe. Its angles do not behave as expected, yet the shape still follows precise rules. Space is flexible, and understanding its curvature allows mathematicians to describe the universe in new ways. This quiet expansion of perspective is meditative, encouraging calm observation and curiosity about how the world can differ from what intuition suggests. Non-Euclidean geometry is not just abstract. It has practical consequences. Einstein used it in his theory of general relativity, showing that the presence of mass and energy curves space. Planetary orbits, light bending around stars, and the behavior of galaxies all reflect this subtle curvature.
The convergence or divergence of parallel paths in space is not just theory. It is observed in the cosmos, reminding us that our universe is quietly complex, elegant, and full of hidden structure. Even in smaller scales, non-Euclidean geometry appears. Curved surfaces in architecture, the shapes of biological forms, and patterns in nature often follow rules of non-Euclidean space. Recognizing these structures encourages a reflective, meditative awareness of order, hidden in seemingly irregular or complex forms. It teaches patience and careful observation, revealing subtle connections that are not immediately visible. Philosophically, non-Euclidean geometry invites reflection on perspective and reality. It shows that what seems impossible in one framework is natural in another. Parallel lines meeting, triangles exceeding 180 degrees, these are not contradictions, but insights into the flexibility of thought and the universe. This gentle challenge to intuition encourages humility, wonder, and thoughtful contemplation. Take a moment to imagine walking along a hyperbolic plane where space stretches infinitely, or an elliptic surface where every path eventually curves toward others. The world feels different, yet consistent, ordered, and calm. Mathematics provides the map, while imagination allows exploration, fostering a reflective meditation on the subtle beauty of space itself.
The geometry of curved space is one of the most subtle and beautiful ideas in mathematics and physics. It asks us to imagine a universe where the familiar rules of flat surfaces do not apply, where straight lines bend and distances stretch in unexpected ways. This gentle shift in perspective quietly transforms the way we understand space, motion, and even reality itself. Take a moment to imagine walking on the surface of a globe. If you start at the equator and walk in a straight line, you eventually return to your starting point. The line seemed straight, but the surface is curved. This is the simplest example of curved space, a two-dimensional surface embedded in 3 dimensions. Yet the concept scales to higher dimensions, influencing the shape of the universe itself. Curved space is central to Einstein's theory of general relativity. Gravity is not a force pulling objects in the traditional sense. It is the bending of space and time caused by mass and energy. Planets orbit stars, and light bends around galaxies, not because of invisible strings, but because space itself curves. Observing this quietly reminds us that the universe is subtle, layered, and full of hidden structure beyond the limits of everyday intuition. Mathematicians study curved spaces using Riemannian geometry, which generalizes the familiar rules of Euclidean geometry. In curved space, the sum of angles in a triangle may not equal 180 degrees. Circles may have different ratios of circumference to radius. Parallel lines may converge or diverge. These gentle deviations from familiar rules are not chaotic. They follow precise mathematical principles, revealing a hidden harmony in the bending of space. Take a moment to visualize this. Imagine drawing a triangle on a smooth, stretched rubber sheet. The angles shift as the surface bends, creating new relationships and subtle patterns. Curved space quietly challenges intuition, encouraging reflection, careful observation, and a calm appreciation of abstract ideas. It is both intellectually stimulating and meditative. Curved space also connects to cosmology, the overall shape of the universe, whether it is open, closed, or flat, depends on the distribution of mass and energy. Observing distant galaxies, measuring the cosmic microwave background, and calculating the trajectories of light all rely on understanding curved geometry.
This quiet connection between abstract mathematics and the vast universe evokes awe, reflection, and a meditative sense of the hidden structure underlying reality. Even in smaller scales, curved spaces appear in surprising ways. Surfaces of biological organisms, the paths of fluids, and the behavior of light in lenses all exhibit gentle curvature. Mathematics allows us to model these systems, revealing order in forms that initially seem irregular or complex. Observing these patterns encourage patience, curiosity, and a quiet appreciation for subtle harmony. Philosophically, the geometry of curved space reminds us that perspective matters. Straight lines, distances, and angles are not absolute. They depend on the shape of the space itself. This invites reflection on perception, relativity, and the limits of intuition. Even our everyday experiences exist within larger, subtly curved frameworks, whether in thought, space, or the universe itself.
Russell's paradox is one of the most intriguing puzzles in mathematics, quietly challenging our understanding of sets, logic, and classification. Discovered by Bertrand Russell in the early 20th century, it reveals a subtle contradiction hidden in the very foundations of mathematical thought. At first, it seems abstract, even strange, but reflecting on it slowly, calmly, and with curiosity can be surprisingly meditative. To understand the paradox, imagine a list of all lists that do not include themselves. Does this list include itself? If it does, then by definition it should not. If it does not, then by definition it should. This quiet contradiction forces us to reconsider how we think about collections, membership, and self-reference. Even simple ideas like a set of sets can hide mind-bending complexities when viewed carefully. Take a moment to visualize this. Imagine a library filled with catalogs. Some catalogs list themselves, some do not. Now focus on the catalog of all catalogs that do not list themselves. It seems impossible to decide whether it belongs on its own shelves. This gentle mental exercise stretches intuition, inviting patience, reflection, and meditative curiosity. It shows that mathematics is not always straightforward. It contains layers of subtle, quiet puzzles. Russell's paradox also highlights the limits of logic. In any system that tries to describe everything, contradictions can arise. Even careful definitions can lead to unexpected outcomes. This is not a failure. It is a reminder that reasoning, while powerful, has boundaries. Logic guides us, but it also challenges us to recognize its edges. There is quiet beauty in noticing where certainty ends and contemplation begins. Philosophically, the paradox encourages reflection on self-reference and circular reasoning. It appears not only in mathematics, but in language, philosophy, and even everyday thought. Sentences that refer to themselves, such as, "This sentence is false," mirror the structure of Russell's paradox. Observing these patterns teaches patience, subtle observation, and a gentle acceptance of ambiguity. Even practical mathematics learned from this paradox. It inspired new approaches to set theory, such as Zermelo-Fraenkel set theory, which carefully avoids contradictions by restricting certain types of self-referencing sets. These adjustments quietly demonstrate how mathematics adapts, reflecting a delicate balance between rules, exploration, and the pursuit of hidden truths. Take a moment to imagine a calm room filled with mirrors. Each reflection shows another reflection, endlessly repeating. Like Russell's paradox, these reflections create layers that seem infinite, challenging simple perception.
Observing them encourages slow, deliberate thought, helping us notice subtle patterns and paradoxes without rushing toward an answer. The paradox also invites reflection on infinity. When we try to classify all objects or all sets, the infinite nature of collections introduces challenges that are impossible to fully resolve with standard logic. This quiet tension between the finite and the infinite, the definable and the undefinable, is both humbling and meditative.
Set theory is one of the foundations of modern mathematics. It studies collections of objects, called sets, and helps mathematicians understand numbers, shapes, and structures in a precise way. Yet, despite its clarity and rigor, set theory contains paradoxes that quietly challenge intuition and reveal subtle limits in logic. Reflecting on these paradoxes is both thought-provoking and calming, inviting patience and contemplation. One famous example is Russell's paradox, discovered by Bertrand Russell in the early 20th century. Imagine the set of all sets that do not contain themselves. Does this set contain itself? If it does, then by definition it should not. If it does not, then by definition it should. This quiet contradiction reveals a deep tension in our understanding of sets and exposes limits in the way we try to classify collections of objects. It is a gentle reminder that even simple concepts can hide subtle, mind-bending complexities. Take a moment to imagine a library of all books. Now imagine a catalog that lists all catalogs that do not list themselves. Does this catalog include itself? Like Russell's paradox, this thought experiment quietly twists logic, encouraging reflection and calm contemplation rather than frustration. It shows that mathematics is not just about rigid rules, but also about exploring the boundaries of thought itself. Set theory paradoxes also appear in ideas of infinity. Cantor's paradox shows that the set of all sets is problematic because it leads to contradictions in size. Infinity, which seems simple and absolute, reveals hidden layers and subtle distinctions. Some infinities are bigger than others. Some collections cannot exist without contradiction. This paradox is quietly unsettling, yet it invites reflective wonder at the richness and subtlety of mathematical thought. Even everyday mathematics is influenced by these ideas. Understanding the structure of sets, their limits, and the paradoxes they contain helps clarify definitions, avoid contradictions, and explore abstract ideas safely. These reflections encourage careful observation, patience, and a gentle curiosity about hidden structures. Take a moment to visualize sets as containers of objects. Some sets can hold themselves, some cannot. Some infinities can be counted, others cannot. The relationships between these sets are subtle, layered, and full of quiet surprises. Reflecting on this structure is calming, as it encourages slow, deliberate thought and meditative contemplation of the unexpected. Set theory paradoxes also connect to philosophy. They ask us to think about classification, truth, and the nature of existence. How can we define collections without contradiction? Can we truly understand infinity, or must we accept its mysteries? These quiet questions encourage reflection, intellectual humility, and patient curiosity. Even in logic, programming, and computer science, set theory paradoxes provide insight. They remind us to carefully define structures, to consider edge cases, and to notice subtleties that might be otherwise overlooked. This quiet attention to detail mirrors the careful, meditative observation that mathematics often requires.
Logic is often seen as the foundation of clear thinking. It guides reasoning, helps us solve problems, and underpins much of mathematics and philosophy. Yet logic itself has limits. Even the most carefully constructed systems can reach boundaries beyond which they cannot provide answers.
Reflecting on these limits is both calming and mind-opening, inviting us to consider the subtle edges of human understanding. One way to understand the limits of logic is through paradoxes. A paradox occurs when reasoning leads to a conclusion that seems self-contradictory or impossible. Consider the classic liar paradox. This statement is false. If the statement is true, then it must be false. If it is false, then it must be true. This simple sentence quietly demonstrates that even logical reasoning can encounter situations where standard rules fail. It invites patience, reflection, and calm curiosity rather than frustration. Another example comes from Gödel's incompleteness theorems. They reveal that in any system of mathematics powerful enough to include arithmetic, there are true statements that cannot be proven within the system itself. Logic is strong, precise, and reliable, yet it has inherent boundaries. Some truths exist beyond proof, quietly reminding us that the universe contains mysteries that may never be fully captured by rules and formulas. Take a moment to imagine building a perfect logical system, one where every truth can be discovered and proven. Now imagine discovering statements that elude proof, no matter how clever your reasoning. This is the quiet beauty of the limits of logic. It is not a flaw, but a reflection of the richness, depth, and infinite possibilities of thought. The edges of logic are spaces of wonder, inviting contemplation and reflection. Even in everyday life, the limits of logic appear. We encounter situations that cannot be resolved by rules alone. Human behavior, ethics, and emotions often defy simple reasoning. Understanding these limits encourages humility. It reminds us that life is more complex than any formula, and that reflection, intuition, and patience are often as important as strict deduction. Logic also meets limits in paradoxes of infinity, such as Hilbert's infinite hotel. No matter how full the hotel appears, there is always room for one more guest. This challenges our intuitive understanding of quantity and shows that even in pure reasoning, imagination and careful thought are required to grasp subtle truths. It is both mind-bending and quietly meditative, inviting a calm awareness of the unexpected. Take a moment to reflect on these ideas. The limits of logic do not diminish its power. Instead, they highlight the beauty and complexity of reasoning, encouraging us to explore thoughtfully, accept uncertainty, and find quiet curiosity in the unknown. Logic is a map, but the world it describes is infinite, layered, and subtly mysterious. Philosophically, acknowledging the limits of logic helps us embrace paradox, uncertainty, and open-ended questions. Some problems may never be fully solved, some truths may remain beyond reach, and some reasoning may lead us in circles. Yet this is not frustrating. It is a gentle invitation to explore, to wonder, and to reflect on the richness of thought itself. Finally, the limits of logic remind us that even in mathematics, philosophy, and science, there are horizons we cannot cross with reasoning alone. These spaces are for contemplation, meditation, and intellectual curiosity. They encourage quiet reflection, patience, and a sense of awe at the infinite subtlety of ideas.
Mathematical proofs are the quiet milestones of human thought. They are more than numbers or symbols. They are carefully reasoned arguments that reveal deep truths about the world. Some proofs have not only solved problems, but have also reshaped how we understand mathematics, science, and even the universe itself. These proofs quietly changed history, offering insight, clarity, and a meditative sense of wonder. Consider Pythagoras' theorem, one of the earliest and most famous proofs. It connects the sides of a right-angled triangle in a simple equation. The square of the hypotenuse equals the sum of the squares of the other two sides. At first glance, this seems like a small, technical statement, yet it has shaped geometry, architecture, and science for thousands of years. It is a gentle reminder that simple truths can have profound, far-reaching effects. Another transformative proof is Fermat's last theorem. For over 3 centuries, mathematicians tried to prove that there are no whole number solutions to the equation x to the power of n plus y to the power of n equals z to the power of n when n is greater than 2. Many thought it might be impossible to prove. Then, in 1994, Andrew Wiles provided a proof that resolved a puzzle that had intrigued minds for generations. This quiet triumph illustrates the patient, persistent, and meditative nature of mathematical discovery. Take a moment to imagine the process of proving a theorem. It requires careful thought, attention to detail, and creativity. Every step builds on the last, forming a chain of logic that is both fragile and beautiful. The proof is not just an answer, it is a journey, an exploration of patterns, structures, and ideas. This journey is calming and reflective, inviting us to slow down and follow the subtle paths of reasoning. Euclid's Elements, another historical masterpiece, provided proofs for hundreds of geometric statements. These proofs established a rigorous foundation for geometry, influencing mathematics, philosophy, and science for centuries. Euclid's work demonstrates that clarity and logical progression can quietly illuminate the world, revealing connections and structures that were once hidden. Proofs also reveal unexpected connections across mathematics. For example, Euler's formula links geometry, complex numbers, and trigonometry in a single elegant equation. E to the power of I pi plus 1 equals 0. This simple equation quietly unites many seemingly separate areas of mathematics, showing that deep harmony can exist even among complex ideas. Observing this unity is meditative, offering a sense of calm insight into the nature of patterns and truth. Take a moment to reflect on the philosophical side of proofs. They show that knowledge is not just discovered, it is built step by step, carefully and patiently. Proofs teach patience, logical thinking, and reflection. They remind us that even abstract ideas have order, structure, and quiet beauty waiting to be uncovered. Mathematical proofs that changed history are not just technical achievements, they are windows into human curiosity, persistence, and insight. They demonstrate that careful reasoning can reveal truths beyond intuition, intuition can be tested, and persistent exploration can yield profound understanding. Each proof is a quiet meditation on the nature of reality, inviting reflection and wonder. Finally, consider the emotional aspect of discovery. The moment a proof is understood, there is a sense of quiet triumph. A hidden truth has been uncovered. A mystery has been illuminated. Mathematics, through its proofs, offers not only knowledge, but also a gentle sense of satisfaction, curiosity, and calm reflection.
The four-color theorem is a quiet but fascinating idea in mathematics. It says that you can color any map, no matter how complicated, using only 4 colors, so that no 2 regions that share a border have the same color. At first, this seems almost magical. How can something so complex be tamed with just 4 colors? Yet, mathematics reveals that even intricate structures can hide elegant simplicity. The story begins in the 19th century, when mathematicians were curious about coloring maps. Imagine a map of countries, states, or regions. How many colors do you need to make sure neighboring areas are always different? Intuition might suggest that some maps would require many colors, perhaps 5, 6, or more. But after years of exploration, it was proven that 4 colors are always enough. This quiet discovery is both surprising and calming, showing that structure and order exist even in seemingly chaotic arrangements. Take a moment to visualize a complex map, full of irregular shapes and borders. At first, it seems impossible to color it neatly with only 4 colors. Yet, if you approach it systematically, you can carefully assign colors to ensure no neighboring regions match. This gentle exercise encourages patience, observation, and thoughtful consideration, revealing the hidden patterns and balance underlying complexity. The proof of the 4-color theorem itself is fascinating. It was one of the first major theorems to rely heavily on computer verification. Mathematicians identified thousands of possible mat configurations and used computers to check each case. This combination of human reasoning and computational assistance quietly demonstrates how different tools can work together to uncover hidden truths. It is a calm reminder that mathematics is not just about numbers. It is about patterns, logic, and creative problem-solving. The theorem also has connections beyond maps. Graph theory, a branch of mathematics that studies networks and connections, uses similar principles. Understanding how to color graphs without conflicts helps in scheduling problems, circuit design, and even understanding social networks. What seems like a playful or abstract idea can quietly illuminate the hidden structures that organize our world. Philosophically, the 4-color theorem encourages reflection on simplicity within complexity. Even in a tangled map of borders, there is an underlying order. Mathematics invites us to notice this order, to step back and see the patterns, and to appreciate the quiet elegance that pervades both abstract and real-world systems. This gentle observation is meditative, calming, and intellectually satisfying. Take a moment to consider this idea in life. Many situations appear complicated at first glance, like a tangled map. Yet, with careful attention and systematic thinking, patterns emerge. Problems that seem impossible can have simple solutions. The 4-color theorem quietly teaches patience, mindfulness, and reflection on the subtle structures that guide reality. Even in nature, similar principles appear. Patterns of veins in leaves, distributions of territories among animals, and networks of rivers all have underlying structures. While these may not directly follow the 4-color theorem, the principle that complex systems can be organized with simple rules resonates broadly. Observing such patterns is calming, offering insight into the hidden harmonies of the world. Finally, the 4-color theorem reminds us that mathematics combines rigor with elegance. It shows that even complicated problems can have beautiful, simple resolutions. This gentle balance between complexity and clarity encourages reflection, curiosity, and quiet wonder.
Topology is a branch of mathematics that studies shapes and spaces in a gentle, flexible way. Unlike geometry, which focuses on precise measurements like lengths and angles, topology looks at how shapes can be stretched, bent, or twisted without breaking. It explores the deeper essence of forms, revealing hidden connections and surprising similarities. One of the most famous examples involves coffee cups and donuts, which might sound simple, but it quietly stretches the imagination and invites reflection. Imagine holding a coffee cup in your hands. It has a handle and a round body. Now think about a donut, a torus in mathematical terms. At first glance, these shapes seem very different. One is for drinking, the other for eating. Yet, in topology, they are the same. You can imagine gently stretching the coffee cup's body and handle without tearing it, and slowly transforming it into the shape of a donut. The hole in the handle becomes the hole in the donut.
This playful equivalence is called topological equivalence, and it demonstrates how shapes can be connected in unexpected, quiet ways. Take a moment to reflect on that. Two objects that seem completely different can, under careful observation, share the same essential structure. Topology encourages us to look beyond appearances, to notice hidden relationships, and to appreciate the subtle connections that weave the world together. It is not just about objects, it is about ideas, forms, and patterns that persist even as surfaces bend and twist. Topology also explores concepts like continuous deformation. A shape can be stretched or compressed as long as it isn't torn or glued in a new place. This gentle flexibility allows mathematicians to classify shapes in new ways, focusing on their essential qualities rather than superficial differences. It is calming to realize that mathematics can be so adaptable, finding harmony and structure in forms that might initially appear chaotic or irregular. Consider other topological ideas like the Mobius strip. This is a surface with only one side and one edge. If you draw a line along it, you return to the starting point without ever lifting your pen. The Mobius strip shows that simple surfaces can hide surprising properties. It is related to the coffee cup and donut example because topology often uncovers unexpected connections between seemingly ordinary objects. Observing these connections is quiet, reflective, and meditative. Topology also has applications beyond playful examples. It helps scientists understand the shape of the universe, the properties of molecules, the structure of networks, and even data patterns in computers. The principles of topology allow us to see underlying forms, continuity, and relationships that are not immediately obvious. It is a gentle reminder that the world is full of hidden structures, waiting to be noticed. Take a moment to visualize transforming a coffee cup into a donut. Stretch the handle, reshape the cup, and watch the whole emerge. You are performing a quiet meditation in your mind, noticing how shapes can change, yet remain fundamentally connected. Topology teaches patience, observation, and wonder. It shows that even everyday objects have hidden relationships and subtle beauty, if only we pay attention. Philosophically, topology encourages reflection on change and perspective. Just as shapes can be deformed without losing their essential properties, life and experience can change while retaining underlying truths. It is a calming thought, a quiet reminder that what matters is not the superficial appearance, but the essential structure, balance, and connectivity that persists through transformation.
Noether's theorem is one of the most profound discoveries in mathematics and physics. It quietly links symmetry to conservation laws, revealing a hidden order in the universe. Named after Emmy Noether, a brilliant mathematician of the early 20th century, this theorem shows that for every symmetry in nature, there is a corresponding conserved quantity. At first, this may sound abstract, but its elegance and simplicity are deeply calming and reflective. To understand Noether's theorem, consider symmetry in time. If the laws of physics do not change over time, if the same rules apply today as they did yesterday, then energy is conserved. This is a quiet, reassuring principle. Energy is neither created nor destroyed, only transformed. The theorem connects this conservation to the symmetry itself, revealing that hidden order governs even the most dynamic systems. Take a moment to imagine a swinging pendulum. As it moves, energy shifts between kinetic and potential forms, but the total energy remains constant. This is a small, tangible example of Noether's insight. The symmetry in time, the fact that the laws of motion do not change, guarantees conservation. Even as things move and change, there is balance and quiet consistency at the core. Noether's theorem also applies to other types of symmetry. Symmetry in space, for example, leads to the conservation of momentum. Rotational symmetry, leads to the conservation of angular momentum. These principles quietly govern the motions of planets, the behavior of atoms, and the unfolding of physical events. Mathematics reveals that symmetry is not just beauty, it is a force that shapes reality, subtly and profoundly. This connection between symmetry and conservation has philosophical depth. It reminds us that hidden structures underlie the apparent chaos of the world. Even in complex systems, quiet laws provide stability. Understanding these connections fosters reflection, patience, and a sense of harmony, as we recognize that order exists even in the midst of apparent unpredictability. Take a moment to reflect on the implications. Noether's theorem tells us that every symmetry carries a hidden gift: conservation. Time, space, and rotation. These abstract ideas are linked to tangible, enduring properties. The universe is not random, it is filled with quiet balances and hidden relationships. This insight is meditative, encouraging observation and appreciation of the delicate structures that sustain reality. Noether's theorem also connects mathematics to physics in a practical way. It helps scientists understand the behavior of particles, the dynamics of fields, and the evolution of the cosmos. Yet beyond its utility, the theorem is poetic. It reveals the quiet, invisible patterns that govern change, showing that simplicity can underlie complexity, and that structure can exist in every corner of the universe. Imagine observing a spinning top. Its rotation is smooth, its momentum conserved. This is not coincidence. It is the result of rotational symmetry, a hidden order expressed through mathematics. The theorem invites us to notice these subtle balances in nature, to find calm and contemplation in the rhythms and rules that quietly structure reality. Finally, Noether's theorem encourages philosophical reflection on the hidden connections between mathematics, physics, and life itself. Just as symmetries govern energy, momentum, and motion, patterns and balances may exist in our daily lives, waiting to be observed. Mathematics becomes not only a logical tool, but also a source of quiet wonder, revealing the underlying order in everything around us.
Symmetry is one of the most beautiful and calming concepts in mathematics. It appears everywhere, quietly shaping patterns, shapes, and structures in both abstract numbers and the physical world. At first glance, symmetry might seem simple, like a butterfly with matching wings, or a perfectly balanced shape. But in mathematics, symmetry has a deeper, almost meditative quality that connects logic, geometry, and even philosophy. In mathematics, symmetry refers to an object or structure remaining unchanged under certain transformations. For example, a square remains the same if you rotate it by 90 degrees or flip it along its diagonal. This quiet regularity is more than just visual beauty. It reveals hidden order, balance, and harmony. Symmetry allows mathematicians to classify shapes, understand equations, and explore patterns in ways that feel intuitive yet deeply profound. Take a moment to imagine looking at a kaleidoscope. The repeating patterns, reflected over and over, create an endless sense of balance and calm. Each rotation, each reflection follows strict mathematical rules, yet the result feels almost magical. Symmetry in mathematics works in the same way. Simple rules give rise to endlessly harmonious structures. It is both logical and poetic, precise yet calming. Symmetry also connects to numbers and equations. Algebraic equations can have symmetrical solutions, and many mathematical functions display symmetry around certain points or axes.
even the concept of parity, whether numbers are odd or even, reflects a kind of symmetry in counting. This subtle regularity encourages reflection and mindfulness, showing that mathematics has order built into its very fabric. Nature, too, reflects mathematical symmetry. Snowflakes, crystals, flowers, and even galaxies exhibit symmetrical patterns. These patterns are not coincidental. They arise from physical laws, growth processes, and chemical interactions. Observing symmetry in nature is soothing. It reminds us that the universe is quietly structured, and that mathematics provides a lens to see the structure more clearly. Take a moment to consider symmetry in motion. Even movements such as walking or swimming can display patterns that repeat in balanced ways. Mathematics captures these rhythms, revealing underlying harmony. Symmetry teaches patience and observation. It encourages us to notice balance in places that might otherwise seem chaotic. Symmetry also has philosophical depth. It represents balance, fairness, and stability. In some ways, it mirrors our desire for calm and order in life. Yet, symmetry is often paired with slight variations or imperfections, creating complexity and beauty. This combination, balance with subtle difference, makes symmetry both soothing and thought-provoking. Mathematicians often study symmetry through group theory, which explores how transformations like rotations, reflections, and translations preserve structure. Group theory connects geometry, algebra, and physics. It shows that symmetry is not just visual, it is deeply logical. Every symmetrical pattern has rules guiding it, and every rule can generate countless harmonious structures. This realization is quietly meditative, revealing that complexity and calm can coexist. Finally, symmetry invites reflection on the hidden order of the universe. Just as we see patterns in numbers, shapes, and nature, symmetry reminds us that there is harmony in the world, even in situations that seem random or chaotic. Mathematics becomes a gentle tool to uncover this harmony, encouraging calm curiosity and quiet contemplation.
The butterfly effect is one of the most poetic ideas in mathematics and chaos theory. It suggests that tiny changes in the starting conditions of a system can lead to enormous differences in the outcome. The name comes from the image of a butterfly flapping its wings in one part of the world, potentially causing a storm somewhere else. At first, this idea may seem fantastical, yet it's grounded in mathematics and helps us understand the quiet complexity of the world. In equations, the butterfly effect appears in systems that are highly sensitive to initial conditions. Even a small adjustment, a fraction of a number, a tiny difference in starting values, can result in dramatically different results as the system evolves. This sensitivity is not random chaos. It is a structured, deterministic process that reveals hidden patterns of growth, change, and unpredictability. The universe through equations can be both orderly and infinitely intricate. Take a moment to imagine a simple weather equation. If you start with slightly different temperatures, pressures, or wind speeds, the solution of the equation might look completely different days later. The change is not due to randomness. It is the natural results of the sensitivity built into the system. The butterfly effect quietly reminds us that small factors, often unnoticed, can have far-reaching consequences, and that the world is a delicate balance of cause and effect. This idea is calming in a subtle way. It teaches patience, observation, and awareness of the hidden variables that influence outcomes. Life, like these equations, unfolds with patterns that are both predictable and surprising. By understanding sensitivity, we can appreciate how interconnected events are and how seemingly insignificant actions or decisions may ripple across time and space. Even simple systems like populations of animals or the motion of planets can exhibit the butterfly effect.
Small fluctuations, amplified over time, create complex behaviors that are impossible to predict precisely, yet still governed by the rules of mathematics. The effect does not mean disorder. Rather, it shows that complexity can arise naturally from simple rules and that careful observation can reveal beauty and harmony in unexpected ways. Consider watching a pendulum swinging. If the pendulum's initial push is slightly different each time, its long-term motion may trace entirely different paths. Each swing is deterministic, yet the pattern is highly sensitive to tiny differences. This quiet unpredictability is not frightening, it is meditative. It encourages reflection on the subtle forces shaping outcomes and invites us to notice the delicate balance between order and variation in the world. The butterfly effect also connects to philosophical reflection. It reminds us that small choices in life can have significant consequences. Our actions, even those that seem trivial, may ripple outward in ways we cannot see. This encourages mindfulness, patience, and awareness of the interconnectedness of all things. Take a moment to visualize this effect. Imagine a single number in an equation being slightly different. As the equation runs forward, its influence grows, touching other parts of the system, subtly shaping outcomes in unexpected ways. Mathematics shows that sensitivity is natural, patterns emerge from simple rules, and complexity can coexist with calm, quiet order.
Randomness is something we encounter every day, from shuffling cards to tossing dice, from raindrops falling on a window to patterns in the stock market. We often assume these events are entirely unpredictable. Yet, in mathematics and nature, what appears random is often governed by hidden rules. This subtle idea, randomness that isn't truly random, invites quiet reflection and gentle curiosity. Take the example of a pseudo-random number generator. When you use a computer to generate random numbers, the results appear unpredictable. A sequence of numbers might look like a series of dice rolls. But if you know the algorithm behind the generator and the starting point, called the seed, you can predict every number in the sequence. The randomness is only apparent. It is a reminder that order can hide beneath apparent chaos, quietly guiding patterns in ways that are not immediately visible. Nature also provides examples of randomness that isn't random. The branching of trees, the structure of crystals, and even the arrangement of galaxies may seem irregular, yet each follows mathematical laws. Lightning strikes, the flow of rivers, and patterns of waves are influenced by physical rules. Randomness exists, but it is framed by structure, constraints, and subtle interactions. Observing this invites calm wonder at the intricate balance between unpredictability and order. Consider the difference between a truly random event and one that only seems random. A coin toss might seem purely chance-driven, but physics determines every detail of the flip: the angle, the force, the air movement, and the spin. If you knew every factor perfectly, you could predict the outcome. The universe is filled with patterns like this, quietly structured beneath the surface of apparent randomness. Take a moment to imagine tossing a handful of sand onto a table. The grains scatter seemingly without pattern. Yet if you could measure every tiny interaction, wind, gravity, friction, you would see that the grains are not random at all. They follow precise physical rules. This realization is calming. It shows that the world is not chaotic in a frightening sense. Rather, it is ordered in ways that are subtle, intricate, and often hidden from our eyes. Randomness that isn't truly random also appears in mathematics itself. Sequences of numbers, such as the digits of pi, seem unpredictable. Yet pi is entirely determined by a simple formula, and every digit follows logically from the previous ones. The randomness is only apparent.
This quiet tension between determinism and unpredictability invites reflection. It reminds us that life, numbers, and the universe can be both surprising and deeply structured at the same time. Even in biology, randomness that isn't random can be seen. Mutations in DNA may appear accidental, yet they follow chemical laws and evolutionary patterns. The spread of populations, the rhythms of ecosystems, and the growth of organisms all contain hidden structure beneath seeming unpredictability. Observing these patterns encourage a patient, meditative appreciation of the delicate balance in nature. Philosophically, this concept asks us to reflect on perception. How often do we mistake hidden structure for randomness? How often do we feel that events are unpredictable when in truth there is order waiting to be discovered? Understanding this subtlety cultivates calm, curiosity, and gentle appreciation for complexity. Take a moment to sit with this thought. The world may feel random, chaotic, or unpredictable, yet beneath the surface, quiet patterns guide everything. Randomness that isn't truly random teaches us patience, observation, and gentle reflection. It reminds us that mathematics, nature, and life are full of hidden layers, waiting to be noticed with calm curiosity.
Coin flips are one of the simplest ways to think about probability. Heads or tails, one chance in two. Yet, even this simple act holds deep lessons about uncertainty, patterns, and chaos. At first glance, a coin flip seems perfectly random, but if we look closer and consider small differences in force, angle, or air resistance, we see that each flip is deterministic in principle, yet unpredictable in practice. This quiet tension between order and unpredictability is at the heart of chaos theory. Chaos theory studies systems that are very sensitive to initial conditions. Even tiny differences can lead to vastly different outcomes. This is often called the butterfly effect. The flap of a butterfly's wings could, in theory, affect weather patterns on the other side of the world. Coin flips provide a simple example. A small change in the starting position or force can make a completely different result, even though the rules of physics are entirely predictable. This creates the appearance of randomness, blending calm determinism with gentle unpredictability. Take a moment to imagine flipping a coin repeatedly. You notice streaks, 3 heads in a row, 4 tails. At first, you might think these streaks are unusual, but chaos theory reminds us that patterns and streaks are natural outcomes of simple, sensitive systems. Even in something as ordinary as a coin toss, complexity emerges from simplicity, showing us that the world is subtle and layered. Coin flips in chaos theory also invite reflection on the difference between what we can predict and what we can observe. In principle, every coin toss follows the laws of physics, but in practice, the outcome appears random. This quiet unpredictability mirrors life itself. Even when we understand the rules, results may surprise us. The paradox is calming, not frightening. It encourages patience and gentle curiosity, reminding us to appreciate the unfolding patterns without needing to control them fully. Chaos theory also connects to larger systems in nature and society. Weather patterns, population dynamics, traffic flow, and even the stock market are examples of chaotic systems. Tiny changes can lead to large consequences, and small patterns can create significant effects. Coin flips provide a simple meditative analogy for these larger, more complex systems. Observing the flip of a coin becomes a doorway to understanding the delicate balance between order and unpredictability in the universe. Consider the patterns that appear when you flip a coin many times. Heads and tails seem random, yet statistical regularities emerge. About half the flips will be heads, half tails over a long series.
Chaos theory and probability work together here. The short-term behavior seems unpredictable, while long-term trends reveal calm order. This duality is quietly fascinating and soothing, showing that chaos and structure coexist in a balanced dance. Philosophically, coin flips and chaos theory invite contemplation of free will, chance, and determinism. Even in a world governed by physical laws, small changes and uncertainties create experiences that feel unpredictable. Life, like a coin toss, is a mixture of order and randomness, structure and surprise. These reflections are gentle, encouraging quiet thought and meditative observation. Take a moment to visualize a coin spinning in slow motion, flipping endlessly. Each toss is influenced by countless tiny factors: force, angle, air currents. No toss is exactly like the last. Yet over time, a subtle balance emerges, a rhythm in the randomness. Chaos theory teaches us to notice this rhythm, to find calm in unpredictability, and to appreciate the quiet complexity in simple actions.
Probability is a concept we encounter every day, yet it can be quietly surprising and paradoxical. At first, probability seems simple. It tells us how likely something is to happen. Flip a coin, and there is a 50% chance of heads. Roll a die, and there is a 1 in 6 chance of landing on any number. But beneath this simplicity, probability hides puzzles and paradoxes that challenge intuition and invite calm reflection. One famous example is the Monty Hall problem, a probability puzzle based on a game show. Imagine there are 3 doors. Behind one is a prize, and the other 2 are empty. You pick a door. The host, who knows what is behind each door, opens another door, revealing nothing. Now you have the choice to stay with your original door or switch to the remaining closed door. Most people think it does not matter, that the odds are equal. But mathematically, switching doors gives you a 2/3 chance of winning, while staying gives you only a 1/3 chance. This paradox shows that probability can be subtle, counterintuitive, and quietly mind-bending. Take a moment to reflect on that. What seems simple at first glance may hide hidden structures and patterns. Probability invites us to think carefully, to slow down, and to notice the rules that govern chance. Even when outcomes feel random, mathematics reveals the underlying order. This gentle revelation is calming, as it encourages patience and thoughtful observation rather than rushing to conclusions. Another probability paradox is the birthday paradox. In a room of just 23 people, there is a better than 50% chance that 2 people share a birthday. This seems surprising because 23 is far smaller than 365 days. Yet when you consider all the possible pairs of people, the likelihood of a shared birthday grows quickly. The paradox reminds us that our intuition about probability often misleads us. It is a quiet lesson in humility and reflection. Probability also appears in nature, science, and daily life. Weather predictions, genetics, quantum mechanics, and even sports all rely on understanding chance. Yet probability can be paradoxical because the world is rarely simple. Rare events happen more often than we expect. Patterns emerge from random sequences, and small changes in conditions can produce unexpected results. These paradoxes encourage us to explore the world with patience and gentle curiosity. Take a moment to imagine flipping coins or rolling dice endlessly. At first, the outcomes seem random, but over time, patterns appear. Probability is not chaos. It is a subtle structure, hidden beneath apparent randomness. It teaches us to embrace uncertainty and to find calm in understanding how chance shapes reality. Probability paradoxes also have philosophical depth. They ask questions about knowledge, prediction, and decision-making.
Can we ever truly know what is likely to happen? How much can we rely on intuition versus mathematics? These quiet questions encourage reflection and thoughtful awareness, inviting us to notice the delicate balance between chance and certainty in life. Even in seemingly simple situations, probability is full of surprises. It reminds us that the world is richer than it appears, and that patterns often exist where we least expect them. This gentle unpredictability is not frightening, it is meditative. It encourages careful thought, observation, and quiet wonder at the hidden structures guiding events around us.
Gödel's incompleteness theorems are some of the most profound discoveries in mathematics. They were introduced by Kurt Gödel, a logician and mathematician in the early 20th century. These theorems quietly changed the way mathematicians understand numbers, logic, and the limits of knowledge. They reveal that even in mathematics, where we often expect complete certainty, there are boundaries to what can be known. The first theorem states that in any logical system powerful enough to describe basic arithmetic, there are true statements that cannot be proven within that system. In other words, no matter how carefully we build a system of rules and logic, there will always be truths that escape proof. This is both surprising and calming. It shows that mathematics is infinite and open-ended, full of discoveries waiting quietly to be uncovered. The second theorem goes even further. It says that no system can prove its own consistency. We cannot use the rules of a system to show that the system itself will never lead to contradictions. This idea may seem unsettling at first, but it encourages humility and reflection. Even the most precise and logical structures have limits, and these limits are not failures. They are gentle reminders of the depth and subtlety of mathematics. Gödel's theorems have implications far beyond mathematics. They show that in any system, whether numbers, logic, or language, there are truths that cannot be fully captured or proven. This connects to philosophy, consciousness, and even the mysteries of the mind. Just as there are limits to formal systems, there may be limits to our understanding of reality. This invites quiet contemplation, patience, and curiosity rather than frustration or fear. Take a moment to imagine building a perfect logical system with every rule carefully defined and every theorem derivable. Now imagine discovering that there are true statements that you cannot prove, no matter how clever you are. This is Gödel's insight. Even in a world of absolute order, there is always a hint of mystery, a quiet space where truth exists beyond our reach. Gödel's incompleteness theorems also highlight the interplay between certainty and imagination. Mathematics is often seen as the ultimate source of absolute truth, but Gödel reminds us that even here, exploration is endless. There are always new truths to discover, new patterns to observe, and new connections to make. This idea is calming in its own way. It invites us to enjoy the journey of learning, rather than insisting on having all the answers immediately. These theorems also encourage philosophical reflection. If there are limits to what can be proven in mathematics, what does this mean for knowledge in general? Are there truths about the universe, consciousness, or existence that we may never fully grasp? Gödel's work reminds us that uncertainty is not a flaw. It is a natural and beautiful part of a complex, infinite world. Take a moment to sit with this idea.
Even in mathematics, where logic seems absolute, there is mystery, depth, and quiet wonder. The theorems invite us to embrace curiosity, to explore patiently, and to appreciate the infinite landscape of thought that stretches beyond proof and certainty. From here, we are ready to explore Turing's halting problem, a related concept that reveals limits to what can be computed or predicted. Like Gödel's theorems, it shows that even in a world of rules, some questions remain unanswered, quietly inviting reflection and contemplation.
Zeno's paradoxes are some of the oldest and most thought-provoking puzzles in mathematics and philosophy. They were created over 2,000 years ago by Zeno of Elea, a Greek philosopher. Zeno wanted to show that our understanding of motion, space, and time can be confusing and even paradoxical. His ideas are not frightening. They are gentle, quiet puzzles that invite reflection and curiosity. One of Zeno's most famous paradoxes is the Achilles and the tortoise paradox. Imagine the swift Achilles racing a slow tortoise. To make the race fair, the tortoise is given a small head start. Zeno asks us to consider this. By the time Achilles reaches the point where the tortoise began, the tortoise has moved a little further. By the time Achilles reaches that new point, the tortoise has moved again. Following this logic, it seems that Achilles can never overtake the tortoise. The paradox is not about speed. It is about how we think about infinity, space, and time. Another famous example is the dichotomy paradox. To travel from one point to another, Zeno argues, you must first reach the halfway point. But before you reach that, you must reach the halfway point of the first half, and before that, the halfway point of the previous half, and so on. There are infinitely many halfway points to cross, so in theory, you never actually reach your destination. This sounds impossible, yet in reality, we move and reach our goals every day. The paradox gently challenges how we understand motion and infinity. Zeno's paradoxes are calm reminders that infinity can be hidden in ordinary experiences. Running, walking, or even thinking involves continuous motion, but mathematics allows us to divide these motions into infinitely small steps. Infinity is quiet, layered, and present even in the simplest actions. Zeno's ideas invite us to slow down and reflect, noticing how subtle and intricate the world can be. Mathematics provides tools to resolve these paradoxes. Calculus, invented centuries later, allows us to sum infinite sequences in a finite way. By understanding limits, mathematicians can show that Achilles easily overtakes the tortoise and that motion across a distance is possible, even if there are infinitely many halfway points. Yet the paradoxes are still fascinating because they highlight deep questions about continuity, space, time, and infinity. Take a moment to imagine dividing a path into smaller and smaller segments. Each step becomes a fraction of the previous one, and yet if you follow the rules of mathematics, the total distance is finite. Infinity does not mean endless impossibility. It can exist quietly within a finite world. Zeno's paradoxes encourage contemplation, showing that our everyday experiences are richer and more complex than they might first appear. These paradoxes also inspire philosophical reflection. If motion seems impossible when broken into infinite steps, what does that say about reality? Are space and time continuous, or are they made of tiny, indivisible units? Zeno's questions are subtle, calming, and quietly challenging. They encourage careful thought, observation, and meditation on the nature of the world. Zeno's paradoxes continue to influence modern mathematics and physics. They touch on ideas in calculus, limits, infinite series, and even quantum mechanics, where motion at the smallest scales is not always intuitive. The paradoxes show that simple questions can reveal deep, hidden truths, and that mathematics allows us to explore these truths with calm curiosity. Take a moment to reflect. Even in something as ordinary as walking or running, there are hidden layers of infinity and subtle questions about motion. Zeno's paradoxes are gentle reminders that mathematics is not only about numbers, it is also about thought, observation, and the quiet mysteries of the world around us.
Cantor's diagonal argument is one of the most elegant and surprising ideas in mathematics. It shows us that some infinities are bigger than others, even though infinity itself seems limitless. This idea may feel strange at first, but it reveals deep truths about numbers, counting, and the infinite, inviting quiet reflection and wonder. The story begins with Georg Cantor, a mathematician in the 19th century. He wanted to understand the size of different infinite sets. For example, the set of all whole numbers, 1, 2, 3, 4, and so on, is infinite. So is the set of all real numbers between 0 and 1. At first, you might think that both infinities are the same size, but Cantor discovered something remarkable. The infinity of real numbers is larger than the infinity of whole numbers. Cantor's method is simple to imagine. Suppose you try to list all real numbers between 0 and 1. You write them in decimal form, one under the other. Then, using a clever trick, Cantor constructs a new number that is guaranteed not to be on your list. He does this by taking the first digit of the first number and changing it, then the second digit of the second number, and so on down the list. The resulting number differs from every number on your list in at least one decimal place. This means no matter how you try, you cannot list all the real numbers. Take a moment to reflect on that. Infinity is not a single concept. Some infinities are bigger than others. The infinity of counting numbers is smaller than the infinity of points on a line. Even in something as abstract as numbers, the universe of infinity is layered, subtle, and profound. Cantor's diagonal argument reveals a hidden hierarchy within the infinite, quietly showing that there are limits to what can be matched or counted. This idea challenges intuition. We often think of infinity as boundless, endless, and uniform, but Cantor's discovery shows that infinity has structure. Some infinite sets are so vast that they cannot be compared directly with smaller infinite sets. This is both fascinating and calming because it reminds us that mathematics allows us to explore ideas beyond the reach of ordinary experience. Cantor's argument also leads to philosophical reflection. If infinity can be bigger or smaller, what does this mean for the universe? Are there infinite worlds, infinite possibilities, or infinite patterns in nature? Even if we cannot see them, mathematics gives us a language to describe and explore these concepts, inviting curiosity and quiet contemplation. Cantor's diagonal argument also connects to other areas of mathematics and computer science. It shows that some problems are inherently unsolvable, that some sets cannot be fully listed or described. This has implications for logic, computing, and even philosophy. The argument is a gentle reminder that not every question has a finite answer, and that some mysteries are endless, inviting patience, reflection, and calm exploration. Imagine looking at a line of numbers that stretches infinitely. You try to capture them all, to write them down, to understand them completely. But there will always be another number, hidden from your view, waiting to be discovered. Cantor's diagonal argument shows that the infinite is not uniform. It has depth, layers, and hidden beauty. This is a comforting and meditative thought. Even within infinity, there is always more to discover.
From here, we are ready to explore the concept of mathematical infinity in paradoxes, where numbers, sets, and infinite sequences lead to ideas that are puzzling, elegant, and reflective. Cantor's work prepares us to see that mathematics is not only logical, but also endlessly mysterious, quietly inviting curiosity and wonder.
Fractals are one of the most fascinating ideas in mathematics. They are shapes that repeat themselves over and over again, infinitely, but they fit inside a finite space. In other words, you can zoom in on a fractal forever, and no matter how closely you look, the same patterns appear again and again. This idea is both calming and mind-bending, showing how infinity can exist within limits. One of the simplest examples of a fractal is the Sierpinski triangle. You start with a large triangle, then remove a smaller triangle from the center. Repeat this process with each smaller triangle. Each step creates more detail, yet the overall shape remains contained. You can continue this process forever, and each level reveals new patterns. This self-similarity, where the whole is reflected in its parts, is a defining feature of fractals. Fractals are not only abstract shapes, they appear in nature. Look at the branches of a tree. Each branch splits into smaller branches, and those smaller branches split again. The pattern is repeated at many scales. Clouds, mountains, coastlines, and rivers also follow fractal patterns. The same rule, repeating a simple process, creates complexity, structure, and beauty in the natural world. Imagine zooming into a fern leaf. The entire leaf has a shape that is echoed in each smaller leaflet, which in turn mirrors the whole pattern. Even though the leaf is finite, it contains infinite detail. This is the magic of fractals. They are a bridge between simplicity and complexity, order and infinity. They show that even in small, quiet spaces, the infinite can exist. Fractals also connect to mathematics in surprising ways. The famous Mandelbrot set, for example, is a fractal created using complex numbers. By applying a simple formula over and over, the Mandelbrot set produces a shape of infinite complexity. The edges are endlessly intricate, yet the overall shape remains contained within a finite area. This shows how simple rules can generate incredible detail, and how mathematics can describe patterns that are both infinite and bounded. Take a moment to imagine this. You are looking at a fractal pattern on a screen, and you begin to zoom in. Each zoom reveals a smaller, repeating structure, endlessly. The process is quiet, meditative, and gentle. Fractals invite us to slow down, observe, and reflect on patterns in both mathematics and life. They show us that repetition, iteration, and patience can create beauty, insight, and understanding. Fractals also have practical applications. They are used in computer graphics to create realistic landscapes, mountains, clouds, and textures. They help model natural phenomena, from the growth of trees to the formation of galaxies. Fractals even appear in medicine, describing structures in the lungs, blood vessels, and brain. They remind us that mathematics is not only abstract, it is deeply connected to the physical world. The infinite nature of fractals is calming in its own way. Even though the detail never ends, the repetition creates harmony and rhythm. You can follow the same patterns over and over, feeling a sense of order and continuity. Fractals are quiet teachers, showing that complexity can emerge from simplicity and that infinity can exist within limits. Reflect for a moment on the paradox of fractals. They are infinite, yet bounded. They are complex,
get generated from simple rules. They are everywhere in nature, mathematics, and even art. Fractals invite contemplation, curiosity, and wonder. They remind us that the universe, and mathematics itself, contains hidden layers of endless beauty waiting to be discovered.
The golden ratio is a number that has fascinated mathematicians, artists, architects, and even nature itself for thousands of years. Its value is approximately 1.618, and it is often represented by the Greek letter phi, or phi. What makes the golden ratio so special is that it appears in so many places, quietly connecting mathematics, art, nature, and the universe. It is a gentle, elegant number that whispers of hidden harmony everywhere we look. The golden ratio is closely linked to the Fibonacci sequence. As the Fibonacci numbers increase, the ratio of one number to the previous one approaches the golden ratio. For example, 21 divided by 13 is about 1.615. 34 divided by 21 is about 1.619. And as the numbers grow larger, the ratio becomes even closer to 1.618. This connection is subtle but profound. It shows that simple patterns can lead to universal constants, patterns that repeat in countless forms across the world. One of the most famous appearances of the golden ratio is in nature. Many plants grow in spirals that approximate the golden ratio, from the arrangement of leaves on a stem to the pattern of seeds in a sunflower. The shells of snails, the horns of certain animals, and even the shape of galaxies often follow spirals related to this special ratio. Nature seems to have discovered a quiet formula for growth, balance, and efficiency, encoded in the language of numbers. The golden ratio also appears in art and architecture. Ancient Greeks used it to design temples, sculptures, and buildings that feel balanced and beautiful. Renaissance artists like Leonardo da Vinci used it in paintings such as the Vitruvian Man to create proportions that are pleasing to the eye. Even modern designers use the golden ratio in logos, layouts, and designs. It is a bridge between mathematics and aesthetics, showing that numbers can create both structure and beauty. Take a moment to imagine a rectangle where the longer side to the shorter side is exactly 1.618. This rectangle feels calm, balanced, and harmonious. If you remove a square from one end, the remaining rectangle has the same proportion. This self-similarity is part of what makes the golden ratio so special. It is infinite in a sense, repeating its harmony no matter the scale, quiet and comforting, like a gentle spiral that goes on forever. The golden ratio also appears in the human body. Many proportions in the face, hands, and body approximate phi. Artists have long noticed that faces and forms that closely follow the golden ratio seem more pleasing or balanced. This does not mean that perfection requires this number, but it does show a subtle pattern underlying life itself. Even music and sound can reflect the golden ratio. Composers sometimes structure pieces using timing or intervals based on phi. Waves and vibrations, too, can exhibit proportions that echo this ratio. The golden ratio connects patterns of space, time, and growth in ways that are quiet, subtle, and deeply mathematical. The beauty of the golden ratio is not just in what it measures, but in the sense of harmony it conveys. It is a number that connects seemingly unrelated things: numbers, nature, art, the human body, and the cosmos. It is a reminder that mathematics is not only logical and precise, it is also elegant, poetic, and quietly present in the world around us. Take a moment to reflect. Everywhere you look, from leaves to shells, buildings to art,
The golden ratio may be hidden in plain sight. It invites calm observation, curiosity, and a sense of wonder. Mathematics, through numbers like phi, shows that beauty and order can emerge from simple rules, connecting everything in a gentle, harmonious way. From here, we will explore the Mandelbrot set, a mathematical object that reveals infinite complexity and beauty. Like the golden ratio, it shows that simple rules can create endless patterns, encouraging reflection, meditation, and quiet fascination.
The Fibonacci sequence is one of the most beautiful patterns in mathematics and nature. It begins simply: 0, 1, 1, 2, 3, 5, 8, 13, 21. Each number is the sum of the two numbers before it. This simple rule creates a sequence that grows endlessly, quietly revealing patterns and harmony throughout the world. At first, it may seem like just a list of numbers, but the Fibonacci sequence connects mathematics, nature, and even art in ways that are both calming and fascinating. One of the most visible expressions of the Fibonacci sequence is the spiral. Take a sunflower, a pine cone, or a seashell. Count the spirals, and you will often find numbers from the Fibonacci sequence. The arrangement is not random. Nature seems to use this pattern to optimize growth, packing seeds, leaves, or petals in the most efficient and balanced way. It is as if nature itself is quietly solving a mathematical problem, creating beauty through simple rules. Imagine watching a snail slowly curl its shell. Each curve is slightly larger than the last, following the proportions of the Fibonacci sequence. The spiral seems infinite, expanding outward in perfect harmony. This spiral is not just beautiful, it is functional. It distributes space efficiently, balances growth, and creates a sense of proportion that is both pleasing and logical. In this quiet way, mathematics and nature meet. Fibonacci spirals also appear in the human body. The arrangement of bones in the hand, the branching of blood vessels, and even the proportions of the face often follow patterns related to Fibonacci numbers. Artists and architects have long used these patterns to create works that feel balanced and harmonious. The sequence is a bridge between mathematics and aesthetics, showing that numbers can create beauty as well as structure. Take a moment to imagine drawing a Fibonacci spiral on paper. Start with a small square, then attach a slightly larger square next to it, and continue adding squares according to the sequence. If you draw quarter circle arcs inside each square, you create a smooth, continuous spiral that grows endlessly. The spiral is calming to look at. It flows gently, expanding without effort, showing how a simple mathematical rule can produce endless elegance. The Fibonacci sequence is also connected to the golden ratio, a number approximately equal to 1.618. The ratio between consecutive Fibonacci numbers approaches this golden ratio as the sequence grows. The golden ratio is another mysterious and beautiful number that appears in nature, art, and architecture. It is closely linked to the spiral, creating curves that feel natural and balanced. This shows that mathematics is not only about rules, it is also about harmony and proportion, about patterns that are both logical and pleasing. Even though the Fibonacci sequence grows infinitely, it never becomes chaotic. Each number follows the simple rule of adding the previous two, yet the results appear in flowers, galaxies, and shells. This duality, simplicity giving rise to complexity, is part of what makes Fibonacci numbers so fascinating.
They are calm, orderly, and deeply connected to the world around us. Think for a moment about the spirals in nature. Each one is unique, yet each one follows the same mathematical rule. They remind us that mathematics is not just abstract numbers on a page. It is a quiet guide, shaping the growth of plants, the curves of shells, and even the rhythms of life. Fibonacci spirals are gentle evidence of the hidden order in the world, quietly waiting to be discovered. Fibonacci numbers also invite reflection on infinity. The sequence continues endlessly, growing larger and larger without ever stopping. Yet each step follows a simple, understandable rule. This balance between the infinite and the comprehensible is calming, showing that mathematics can be both vast and approachable, mysterious and comforting.
The Riemann hypothesis is one of the most famous unsolved problems in mathematics. It is connected to prime numbers, the building blocks of all numbers, and to deep patterns hidden in the number line. The hypothesis is named after Bernhard Riemann, a German mathematician who lived in the 19th century. He discovered a surprising connection between primes and a special kind of function, now called the Riemann zeta function. His insight opened a doorway into patterns that are invisible to the eye, but revealed through mathematics. At its heart, the Riemann hypothesis suggests that the distribution of prime numbers follows a hidden order, one that can be described by complex numbers. Prime numbers seem scattered and unpredictable at first, but Riemann discovered that their spacing is linked to the zeros of his zeta function. These zeros are points in the complex plane where the function equals 0. Riemann proposed that all these critical zeros lie on a straight line in the complex plane. This simple-sounding idea has profound consequences. If it is true, it explains why primes appear as they do and provides a deep insight into the structure of numbers. Imagine standing at the edge of a calm, infinite ocean. The surface appears chaotic, with waves moving in all directions. But beneath the surface, there may be hidden currents, invisible patterns that guide the motion of the water. The Riemann hypothesis is like discovering those hidden currents in the ocean of numbers. It suggests that beneath the apparent randomness of primes, there is a quiet, elegant order waiting to be understood. Even today, over 150 years after Riemann proposed it, mathematicians have not been able to prove the hypothesis. Many zeros of the zeta function have been checked, and all of them lie on the critical line, just as Riemann predicted. But no one has yet shown that this is true for all zeros, infinitely many of them. This unsolved problem remains one of the deepest mysteries in mathematics, quietly inviting exploration, thought, and wonder. The Riemann hypothesis is not just abstract theory, it has practical implications in number theory, cryptography, and computer science. Prime numbers are used to encrypt data, and understanding their distribution could improve algorithms, make communication more secure, or even reveal unexpected connections in mathematics. It shows that even the most theoretical ideas can have real effects, quietly influencing the world in ways we might not immediately notice. Take a moment to reflect on this. A single idea proposed over a century ago can connect numbers, infinity, and complex functions. It shows us that the universe of mathematics is vast, quiet, and full of patterns. Even when we do not fully understand it, we can explore it slowly, thoughtfully, and calmly. The Riemann hypothesis invites patience, curiosity, and reflection, reminding us that the journey of discovery can be as beautiful as the answer itself. The hypothesis also invites philosophical contemplation. It raises questions about order and randomness, certainty and mystery. Are the primes scattered by chance, or do they follow a hidden plan? Is mathematics something humans invented, or something we discovered, existing independently in a silent, infinite realm?
These questions have no immediate answers, but they encourage quiet wonder and introspection, like gazing at stars in the night sky. The Riemann hypothesis, like many unsolved problems in mathematics, shows that even in a world of logic and rules, there is room for mystery, imagination, and awe. It shows us that mathematics is not only a tool, it is a way to explore the infinite, the unseen, and the quietly beautiful structures underlying reality.
Prime numbers are numbers greater than 1 that can only be divided by 1 and themselves. Numbers like 2, 3, 5, 7, and 11 are prime. At first, they may seem simple, just a list of numbers, but prime numbers are some of the most mysterious and fascinating objects in all of mathematics. They are the building blocks of numbers, the foundation on which all other numbers are made. Every number greater than 1 can be created by multiplying primes together. In this sense, primes are like the atoms of mathematics. Primes have been studied for thousands of years. Ancient mathematicians noticed patterns in them, but these patterns are strange and elusive. There is no simple formula that tells us where the next prime number will appear. They are scattered along the number line like stars in the night sky, sometimes close together, sometimes far apart. And yet, even in their apparent randomness, primes have deep order and structure that mathematicians continue to explore. Take a moment to think about that. Simple numbers like 2 or 17 hide infinite mysteries. As numbers grow larger, primes become more rare, yet they continue forever. There is no largest prime. You can always find a bigger one if you search long enough. Infinity is woven into the very fabric of prime numbers, making them both simple and endlessly complex at the same time. Primes are also connected to the modern world in surprising ways. They are used in cryptography, the technology that keeps our digital information safe. Without primes, computers could not encrypt messages, passwords, or financial transactions. The patterns of primes, which may seem abstract and theoretical, have very real consequences in our daily lives. Mathematics, even in its quietest corners, has a profound impact on the world. Yet primes are still mysterious. Mathematicians have discovered many interesting properties. For example, twin primes are pairs of primes that differ by just 2, like 11 and 13, or 17 and 19. Some mathematicians wonder if there are infinitely many twin primes, but no one knows for certain. Other questions, like the Riemann hypothesis, explore deep connections between primes and patterns that extend into infinity. These questions remain unsolved, quietly challenging human understanding. Primes also have a kind of beauty that is hard to describe. They appear in nature, in music, in patterns of life. Their unpredictability, combined with their fundamental importance, gives them a mysterious elegance. Prime numbers remind us that even the simplest things, counting numbers, can contain infinite depth. They are quiet, profound, and endlessly fascinating. Take a moment to imagine the prime numbers stretching along the number line. You cannot see them all at once, and yet you know they continue forever. Their distribution is not random, but it is not simple either. There are patterns that emerge only when you look carefully, and these patterns hint at deeper truths about mathematics and the universe. Primes are a reminder that there is always more to discover, always another mystery waiting just beyond what we can see. Primes also invite philosophical reflection. They challenge our intuition about order and chaos, simplicity and complexity. They show that even in something as basic as counting, there can be endless surprise. Every prime is a quiet monument to the infinite, a single point on an endless number line that stretches forever. From prime numbers, we are ready to step into the Riemann hypothesis, one of the greatest unsolved mysteries in mathematics.
This hypothesis explores hidden patterns in primes, connecting them to complex numbers, infinity, and the structure of mathematics itself. It is a doorway to deeper understanding, inviting us to explore both the calm and the mystery of the number world.
The uncertainty principle is a strange and fascinating idea. It comes from physics, but it is deeply connected to mathematics. At its heart, the principle says that there are limits to how much we can know about certain things at the same time. For example, in quantum mechanics, we cannot know both the exact position and the exact speed of a particle at the same time. The more precisely we know one, the less precisely we know the other. This idea might seem strange, but it shows that the universe has built-in uncertainty, and mathematics helps us understand it. Even though this principle comes from the microscopic world of particles, we can think about it in simpler terms. Imagine trying to measure a moving car with a ruler. The more closely you measure its position at one moment, the harder it becomes to know exactly how fast it is moving. At very small scales, this uncertainty is not just a limitation of tools, it is a fundamental part of nature. The universe itself has boundaries to what can be known, measured, and understood. Mathematics is what allows us to describe this uncertainty. Using equations, probabilities, and functions, mathematicians and physicists can predict the likelihood of where a particle will be or how it will behave. Even when precise certainty is impossible, patterns emerge. Mathematics becomes a language for exploring the unknown, giving us calm understanding in the face of mystery. Take a moment to imagine this. You are watching tiny particles, too small to see, moving in ways that seem random. You cannot predict their exact paths, but you can predict their overall behavior. The universe is not chaotic, it is probabilistic. Mathematics provides the framework to navigate this uncertainty, to find order within what seems unpredictable. The uncertainty principle also invites philosophical reflection. If we cannot know everything about even the smallest things, what does this mean for knowledge? What does it mean for reality? It suggests that the universe is not fully determined, not fully predictable. There are limits to what can be observed, measured, and understood. But this limitation is not frightening. It is gentle and contemplative. It reminds us that curiosity is more important than certainty, and that exploration is valuable even when the answers are incomplete. Uncertainty in mathematics also appears in other ways, such as in limits and approximations. Calculus, for example, deals with changing quantities and approaching values that cannot always be exactly reached. Complex numbers, probabilities, and infinite sequences all help us manage uncertainty. Even when absolute precision is impossible, mathematics gives us a way to understand, predict, and navigate patterns in the world. Take a moment to breathe and reflect. The universe is vast, full of uncertainty, and full of hidden patterns. Mathematics is not just a tool for exact answers, it is a gentle guide that helps us explore the unknown, appreciate its beauty, and find comfort in understanding what can be known. Even in the presence of uncertainty, there is order, there is logic, and there is quiet wonder. The uncertainty principle also connects to the idea of limits in mathematics. Some things cannot be known perfectly, but we can approach them as closely as we like. This idea encourages patience and mindfulness. It reminds us that even in complexity, we can find understanding, calm, and insight. From the uncertainty principle, we move toward prime numbers, which are simple yet deeply mysterious. Prime numbers are the building blocks of mathematics, but they follow patterns that are still not fully understood. They show us that even within order, there is mystery, and that some questions may never have complete answers. These patterns, hidden in the integers, are quiet, infinite, and waiting to be explored. Imaginary numbers are strange, even by the standards of mathematics. They do not exist in the world the way normal numbers do. You cannot hold them in your hand, count them on your fingers, or see them in everyday life. Yet they are very real in mathematics, and they have powerful uses in science, engineering, and technology. The most basic imaginary number is called I. It is defined as the square root of -1. This seems impossible at first. In ordinary math, no number multiplied by itself gives a negative result. 2 times 2 is 4. -2 times -2 is also 4. There is no number that times itself equals -1. But mathematicians imagined a new number to solve this problem, and they called it I. Imaginary numbers sound like they are just fantasies, ideas that exist only in the mind. And in a way, they do. But they also have real effects. When combined with ordinary numbers, they form complex numbers. A complex number has two parts, a real part and an imaginary part. For example, 3 plus 2i is a complex number. These numbers can be used to solve equations that cannot be solved with ordinary numbers. They allow mathematicians to explore a world that goes beyond what is visible and tangible. Imaginary numbers are not only useful in abstract mathematics. They describe waves, electricity, and signals. Engineers use them to design circuits, control systems, and sound waves. Physicists use them in quantum mechanics to understand the behavior of particles that are too small to see. Imaginary numbers allow us to model the invisible and the intangible, giving us a bridge between thought and reality. Imagine for a moment a world without imaginary numbers. Many of the technologies we take for granted, radios, computers, televisions, and cell phones, would not exist. We would be unable to fully understand the behavior of light, sound, or electrons. Imaginary numbers may seem strange, but they are deeply practical. They show us that sometimes what seems impossible can be the key to understanding the world. The word imaginary may make these numbers sound unreal, but they are as consistent and logical as ordinary numbers. They follow rules, can be added, subtracted, multiplied, and divided, and they fit into a larger system called the complex plane. In this system, numbers are plotted on a grid, where one direction represents real numbers and the other represents imaginary numbers. This plane allows mathematicians to visualize and explore concepts that would otherwise be invisible. Take a moment to reflect on this. Numbers that cannot exist in the ordinary sense, numbers that are imaginary, have power. They shape the way we understand the universe, allowing us to explore ideas that go beyond what is tangible. They remind us that imagination is not separate from logic. Sometimes the most abstract ideas can reveal the deepest truths. Imaginary numbers also invite philosophical reflection. If numbers that cannot exist in the normal sense can describe reality so accurately, what does this say about the universe? Does the universe follow rules that are invisible to our senses? Are there truths that exist beyond what we can see or touch? Imaginary numbers suggest that mathematics is not just a tool invented by humans, it is a language of patterns.
one that can describe both the visible and the invisible aspects of reality. From imaginary numbers, we can move further into the world of complex numbers, waves and oscillations. We can see how mathematics models movement, change, and the behavior of systems too small or too large to experience directly. Imaginary numbers open the door to thinking in new dimensions, to imagining spaces that exist beyond our ordinary perception, and to exploring patterns that are both beautiful and mysterious.
Some numbers never end. They go on forever, without repeating, without settling into a simple pattern. These numbers are called irrational numbers. Unlike 1, 2, or 3, which can be written as simple fractions, irrational numbers cannot be expressed as one number divided by another. They are endless, mysterious, and strange, yet they appear everywhere in mathematics and in the world around us. The first known irrational number was discovered over 2,000 years ago by the ancient Greeks. They were trying to measure the diagonal of a square with sides of length 1. If the sides are 1, then the diagonal should be a number that can be written as a fraction, they thought. But when they tried, they found it was impossible. The diagonal's length could not be written as one number divided by another. This number, now known as the square root of 2, stretches on forever without repeating. Irrational numbers are not just a curiosity. They appear in many places in nature. The number pi, which describes the ratio of a circle's circumference to its diameter, is irrational. It goes on forever, 3.14159, and never repeats. The golden ratio, which appears in flowers, shells, and even galaxies, is also irrational. Irrational numbers are hidden in the patterns of the world, quietly shaping the shapes and rhythms of nature. These numbers are strange because they are both predictable and unpredictable. We know they exist, we know they're valued to as many decimal places as we like, but we can never write down all the digits. They are endless. Imagine trying to write pi completely. You could write for your entire life and still not finish. Irrational numbers remind us that there are limits to what we can know, limits to what we can measure, and limits to what we can imagine. Take a moment to think about that. Even in something as simple as a number, there can be endless mystery. Irrational numbers are quiet, hidden, and infinite. They exist all around us, in the circles we draw, in the spirals of a snail shell, in the proportions of a leaf. They are a gentle reminder that even in order, there's surprise. Even in mathematics, there's wonder. Irrational numbers also lead us to questions about completeness. Can we ever fully know a number? Can we ever truly capture something that goes on forever? They challenge our sense of certainty and push us to accept that some things are endless, infinite, and unreachable, at least by human hands. Yet they are not frightening. They are calm, quiet, and beautiful, like a river that flows without end or a star that shines endlessly in the night sky. Some irrational numbers are more famous than others. Pi is the most well-known, appearing in circles, spheres, and waves. The square root of 2 appears in geometry and architecture. The golden ratio appears in art, nature, and design. All of these numbers have one thing in common. They are infinite. They cannot be written as a simple fraction. And they connect the abstract world of mathematics to the real world we experience every day. Even in simple equations, irrational numbers show their power. They appear in formulas for growth, decay, and motion. They describe the behavior of waves, sound, and light. They're part of the hidden language of the universe, quietly shaping the patterns we see and those we cannot see. Irrational numbers also prepare us for more complex ideas, like complex numbers, which combine real and imaginary numbers to describe waves, electricity, and quantum mechanics. They are part of a journey from the simple world of counting in zero into the endless, strange, and beautiful universe of mathematics. Take a moment to reflect. The next time you draw a circle, notice a spiral, or watch a wave, remember that irrational numbers are at work. They are quiet, infinite, and mysterious,
connecting simple ideas to infinite possibilities. They show us that mathematics is not just about rules and answers. It is about curiosity, wonder, and exploring the endless mysteries of the mind and the universe. Infinity is one of the strangest ideas in mathematics. It is not a number you can count to. It is not a place you can reach. It is an idea, a concept of something that never ends, something without limit. Infinity appears in many places in math, in counting, in shapes, in sequences, and even in the strange worlds of calculus and probability. But it is also something that can feel mysterious, even unsettling, because it challenges the way we think about numbers, space, and reality. Imagine a hotel with an infinite number of rooms. This hotel is completely full. Every room is occupied. One might think that means there is no space for anyone else. But in the world of infinity, there is always room for one more. The manager can move each guest to the next room, opening up the first room for a new visitor. Even if 100 new guests arrive, or 1,000, or an infinite number of guests, the hotel can always find space. This strange idea is called Hilbert's infinite hotel, and it shows that infinity behaves very differently from normal numbers. Infinity also exists in sequences of numbers. Think of counting: 1, 2, 3, 4, and so on. You can keep counting forever. There is no largest number. No matter how high you go, there is always one number higher. Infinity stretches endlessly, beyond our imagination. And yet, infinity is not chaotic. Mathematicians can study it carefully, discovering patterns, relationships, and rules that govern this endless world. Infinity is strange, but it is not random. One mind-bending idea about infinity is that there can be different sizes of infinity. For example, the set of all whole numbers, 1, 2, 3, 4, and so on, is infinity. But the set of all points on a line, all fractions between 0 and 1, is an even bigger kind of infinity. There are more points on the line than there are counting numbers. This seems impossible, but it is true. Infinity is not just big, it is complicated. Some infinities are bigger than others, and mathematicians have spent centuries studying these differences. Infinity also connects to the mysteries of the universe. In physics, scientists talk about infinite space, infinite time, and infinite possibilities. In mathematics, infinity appears in equations, limits, and the behavior of curves and functions. Infinity shows us that some things cannot be measured in the usual way. It reminds us that there are questions that have no end, problems that have no final solution, and ideas that stretch forever. Take a moment to think about this. Imagine a line stretching endlessly in both directions. You can walk along it, but you will never reach the end. You can try to count all the numbers along the line, but there are always more numbers beyond the ones you have counted. Infinity is both comforting and strange. It tells us that the world is larger than our minds, but it also gives us patterns and rules to explore this vastness carefully. Infinity also appears in paradoxes, ideas that seem to break the rules of logic. One famous example is Zeno's paradox of Achilles and the tortoise. Achilles runs a race with a tortoise that has a small head start. To reach the tortoise, Achilles must first reach the point where the tortoise began. But by the time he reaches that point, the tortoise has moved a little further, and so on, infinitely.
At first, it seems Achilles can never catch the tortoise. In reality, he can, but the paradox shows how infinity can create surprising problems, even in something as simple as running. Infinity forces us to think differently. It teaches patience, curiosity, and wonder. It reminds us that there are things beyond counting, beyond measurement, beyond our everyday understanding. Infinity is not scary. It is quiet, vast, and mysterious, like staring at the night sky or imagining the endlessness of time. From infinity, we begin to explore numbers that are both simple and strange, the irrational numbers. These numbers go on forever without repeating, like the square root of 2 or pi. They are connected to infinity in a very deep way, stretching endlessly, showing patterns and beauty that are both comforting and mysterious.
Dividing by zero is one of the strangest ideas in all of mathematics. At first, it seems simple. We know how to divide numbers. 6 divided by 2 is 3. 10 divided by 5 is 2. But what happens if you tried to divide a number by 0? 6 divided by 0? 10 divided by 0? Suddenly, the rules of math break down, and the result becomes mysterious, even impossible. To understand why, imagine you have 6 apples, and you want to share them with friends. If you have 2 friends, each friend gets 3 apples. If you have 3 friends, each friend gets 2 apples. But if you have 0 friends, how many apples does each friend get? There is no answer. The question doesn't make sense. Dividing by 0 is like trying to share something with nobody. It is a simple question that has no simple answer. Mathematicians say that division by 0 is undefined. This means that it cannot be calculated, it cannot be solved, and it does not exist in the rules of math. But this simple impossibility leads to some very strange ideas. When we divide by a number, smaller and smaller, getting closer to 0, the answer grows larger and larger. For example, 1 divided by 0.1 is 10. 1 divided by 0.01 is 100. 1 divided by 0.001 is 1,000. If we divide by 0 itself, the answer would be infinitely large. Infinity appears when we divide by 0, and infinity is a concept that is difficult to imagine. Infinity is not a number you can hold or write in full. It is a concept, an idea of something that never ends. Dividing by 0 gives us a glimpse of infinity, showing us how mathematics can reach beyond the limits of our everyday understanding. Even though division by 0 is impossible, it points us toward new ways of thinking about the universe, space, time, and numbers themselves. The impossibility of dividing by 0 also challenges our sense of reality. In the real world, nothing can be divided by nothing. But in mathematics, we can imagine it. This is one of the powers of math. It allows us to explore impossible ideas safely, in our minds, using symbols and rules. We can think about infinity, nothingness, and paradoxes without danger. Math becomes a playground for the imagination, a place where the impossible can be studied carefully and calmly. Dividing by 0 also connects to other strange concepts like limits, calculus, and the edge of numbers. Mathematicians developed special ways to study what happens as numbers get very small, very close to 0, without actually dividing by 0. These methods let us explore infinite processes, curves, and changing systems. Even though we cannot divide by 0 directly, the idea leads to some of the most powerful tools in mathematics, helping us understand motion, growth, and change. Take a moment to imagine infinity. Stand at the edge of a number line and think about what happens as numbers get larger and larger. There is no end. Infinity stretches endlessly, beyond counting, beyond imagination.
Dividing by zero gives us a doorway into this infinite world. Even though we cannot step inside completely, we can approach it, observe it, and feel the strange thrill of thinking beyond the limits of our minds. Dividing by zero also is a gentle reminder of limits. There are things in mathematics and in life that cannot be forced or solved. Some questions do not have answers. Some problems do not have solutions. This can be uncomfortable, but it can also be peaceful. It teaches patience, acceptance, and curiosity. We can explore what is possible while respecting the boundaries of what is impossible. From zero and division by zero, we are ready to step further into the unknown. We are prepared to meet infinity in new forms and to encounter the paradoxes that challenge our understanding of numbers and reality. These paradoxes are not problems to be solved quickly. They are mysteries to be experienced slowly, gently, like drifting into a quiet, infinite space.